Right, so we're looking at adjacency matrices. This is lesson 3. Let's get started. Right, 3 things you need to be able to do: construct graphs or networks from adjacency matrices. We'll talk about what this actually means in a second. Do the opposite of what we just said and produce and interpret multi-stage adjacency matrices from the adjacency matrices. So again, we'll talk about what this means. There's a few key moments within this that you need to make sure that you understand as well. So I'll cover those in depth. So, what is an adjacency matrix? Basically, what it is summarizing all of the edges that you see within a network. Okay, so a matrix, like I said, can be used to summarize it all, and what we do is we represent this in terms of an adjacency matrix. So, what we have is over on the left-hand side, we have from, and we have to. Okay, first thing is I would be putting these in alphabetical order from A, B, C, D, E, and across the top A, B, C, D, E. All right. So what this means is that keep them in the same order. All right. Don't mix up the order. Don't have A, B, C, D, E, and then across the top E, D, C, B, A. Right. Makes no sense. So just make sure you keep them in the right order. Now, second thing is it's always going to be a square matrix here because you've got the same number here as the same number across the top. All right. So it's always going to be a square matrix here. This one being a 5 by 5. All right, so basically what you're trying to do, the way that each of these numbers are in fact derived, is trying to figure out how you get from A, so reading this as from A to A. Now you cannot get from A to A in one of the edges, right? It's not possible. You have to pass to B, or you have to go to C, or you have to go to E. Right, so it's not possible to get from A to A in one step. Now, when I say one step, basically it means across one edge. A to B is, however, possible. So A to B, that represents this line here, right? So you'd go A to B, that is one way of getting from A to B. Okay, as you continue through this, A to C, right? A to C, there is one way of doing that. A is not connected to D because there's no direct connection to D. And A to E, there is one connection going down here. You then complete this. Now we're leaving from B to A. So B to A, there is one connection, one road. B to B, well, B is not connected to itself through a loop. B to C. Now B is connected to C by multiple edges. So we have one across the top, but we also have one going through here as well. Hence, we put the number 2. There's 2 ways of getting from B to C. B to D, etc., etc. Okay, so what we have is this is how we produce the matrix. All right, we're going to talk a little bit more in depth about this in a moment. Okay, here we go. Like we said, it's a square matrix. It has 5 rows and 5 columns. Rows go across, columns go vertically. Okay, in each of the different locations is we have a number which represents how many ways there are in fact to get from and to each of those locations. All right, as we just said, right, making sure you're putting a number in for each of these. A 0 at the intersection of row A and column A because there is no edges connecting A to itself. That is, there is no loop at vertex A. Okay, so that was talking about that one just there. All right, let's continue. A 1 at the intersection of row A, column B because there's one edge connecting A to B. All right, a 2 at the intersection of C to B because, as we just said before, there are 2 edges connecting C to B. All right, let's keep going. That was talking about that, and that too, we were talking about that one just there. All right, moving on. Now we want to do the opposite skill to what we've just spoken about. Okay, so draw a graph given the adjacency matrix given. Okay, so remember is that on this side is we have from, and above here we have to. So in other words, A to A is 0. A is not connected to itself. A to B is 0. A to C is connected twice. So what we can then do is we can then connect A to C twice, right? So that has just ticked off those 2 lines there. As we continue through, A to D is none, and A to E is connected once. So I go across each of the rows, Then I go down and start on the next one. B to A is not connected. B to B is not connected. B to C is connected twice. So I need to draw in 2 lines there. B to D is connected once. So again, I need to draw a line there, like so. Next row. C to A is connected twice, as we've already done. C to B is connected twice, as we've already done. Continue through. C to D is connected once, so I need to construct a line. And as I continue through, D to B is already connected. D to C is already connected. D to D. Now there is a 1 here. So that means it needs to create a loop upon itself. E to A is 1, alright, as it is already connected. So that is how we draw the adjacency matrix, or given the adjacency matrix, that's how we draw the graph or network. Alright, go through each of the rows one by one and constructing them like so. Now that's quite an easy one, because now what happens is that we have, in fact, a directed graph. This example of what we did was an undirected graph. Now an undirected graph was a nice example of the one we just had before, because there were no arrows on the diagram. As soon as I put an arrow on the diagram like so, that indicates I can only drive from B to D. So in relationship to my matrix, which I've got here, that means B to D would still be 1, so that number there would still be 1. However, B back to D, this one is not possible. So I would have actually put that as 0. All right, if I was to make that directed. It's obviously not directed here, so I don't need to worry in this example. We'll see a later example where that will in fact happen. Okay, so undirected graphs, what we have is we have the leading diagonal running across. Now you would have done this in apps last year as well. If there is symmetry about this, so if I picture this as my symmetry line, right, so that is symmetry to that is symmetry to that, and we can see my symmetry lines going like this. So see within each of these, they are all symmetrical, not just the outside ones, but also the ones internally. So the 1 matches up with the 1, 1, 0, 1, 2, 2, they all match up. Given we have symmetry within this, what it actually means is it means that it is in fact undirected. Okay? As soon as we don't have symmetry within our symmetry line across our leading diagonal, it means that it is in fact a directed graph. Okay? So, a directed graph, or sometimes called a digraph. Here is an example of a digraph. We have directions. Now you don't need to have directions across every single line. You don't need to. Alright? So with this one here, right, is that we have directions on every single line. You don't actually need to do that. In actual fact, when you look at this example right here, could you simplify that? So as opposed to having 2 roads that go one that way, one that way, could you not just change that to just one road without a direction? Wouldn't that just mean the same thing? Yeah, so you could actually just simplify that back to one road without a direction. It all means the same. Okay? Right, directed graphs, right, all the edges, all the arcs have arrows on them, indicating the direction of flow, like one-way streets. Right, so for this example, we can see in a directed graph, it might be possible to go from A to B, but not B to A, okay, because the direction is going only in that one way. Now, how does this then affect the adjacency matrices? So, you then need to be careful of how you do this. It does change it a little bit. Firstly, now along its leading diagonal, which here, we can now see that they don't match up. The 1 does not match up with the 0. Immediately, as soon as 1 doesn't match up, it indicates it is in fact directed. Across this one, that's all okay, it all matches up, not that it really matters. Here, I have another example where it doesn't match up, symmetrical, symmetrical. So I've got 2 examples of here where it is not symmetrical, and that is indicating it is in fact directed graph. So you should be able to identify a directed graph from the matrice itself. Right, and as we said, it won't be symmetrical across its leading diagonal. Okay, multi-stage matrices. So if we have something like this, right, a directed graph, because we see the arrows, we could in fact summarize each of these. So Raquel to Raquel. Now, she does not connect to herself, so we put a 0. Raquel to Eleanor. Now, she connects in one way, through that red line there. Raquel to Darmini connects in 2 ways, those 2 red lines across the top. Raquel to Pia connects in 1 way, in that red line, etc. We now go from Eleanor and summarize all of hers. Eleanor connects to Raquel in a 1 way. Eleanor connects to herself in 1 way, to Darmini in 0, etc. Okay, so we can go through and plot each of these. So that was what we have in terms of, we call this a 1-step. Now, 1-step means that you directly connect to these people, right? Directly through one edge. In other words, you pass over one edge to connect to the new vertice that you want to go to. So now what happens is that within this 1-step, if it's not possible, we could then consider a 2-step equation. In other words, we've got a path of 2. Now, path is a definition we'll get to a little bit later on. In other words, that if you wanted to deliver a message, right, we could say that Raquel wanted to deliver a message through to Pia through Darmini. All right, so that means she will go to Darmini first and then she will go down to Pia. So what we're trying to do is we're trying to consider this as a 2-step equation, or 2-step from here. Right, we're doing Eleanor to Darmini. So that could be done in this green way, right, following that arrow there, right? It could also be done in the blue way, going across the top, or we could go through Pia across the bottom there. So the number of ways that we could now get from E to D, right, previously didn't connect directly, but in 2-step, you were able to do that in 3 different ways. So to create a 2-step equation, what you are simply going to do is you're going to square the matrix. Now, you don't actually need to know how to do this manually. All you need to know how to do is put this into your calculator. So you take your matrix like so, all right, and you're going to square it. So within my matrices, right, main mode, keyboard, math 2, when you click on this, it adds columns. When you click on this button, it adds rows. Now for everything we're going to do, it's going to be a square matrix, so probably just better off using this, and it just keeps on adding rows and columns in the same rate. All right, you can use clear to clear things, etc. So you're going to type the original matrix in exactly how it appears, 0, 1, 2, 1, 0, 1, 2, 1, etc. across like so, and that is obviously equal to itself if you put push EXE. Now, if we want the 2-step equation, what we're then going to do, right, we take the matrix itself and we put it to the power of 2. Right, we square it. That will tell you what the 2-step is for this. So the 2-step is now from, in order, we had of R, E, D, P, R, E, D, P, all of these, they all correspond to 2-step from each of those. Right, so in other words, how is this number 1 generated just here, R to R? The one way you could go from R to R is you would go down to E and then you'd go back up. That is one way of getting from R to R. There is no other way of doing that in 2 steps. In other words, passing over 2 edges. If we looked at another one, let's try R to P. So let's try this one. There are 3 ways of doing that. So here is one way, going across the top and down, one way. A second way would be going across to D and then down, that is 2. And the third way would be going down to E and then across to P. There are 3 ways of doing that, hence we have the number 3. So in other words, you're going through a third person, right? That is a 2-step. All right, etc., etc. All right, so I've just spoke about that one right there. That's visible within matrix M squared, so on and so forth. Okay. Last slide. Symmetry across the leading diagonal indicates it's undirected. Okay, don't have to include arrows. All right. If there is in fact a number on the leading diagonal as a last note, it indicates there is in fact a loop. All right, and you can see that loop here, which is one thing we didn't mention. Perfect. That is it. Good luck. Give the exercise a go.